Thanks for joining me today as we are going to do a little bit of training on demulsifier treatments for diesel fuel. I am Eric Bjornstad, and I'm Technical Information Director for Bell Performance. And our goal today is that we want to have a better understanding of a number of things having to do with the need for demulsifiers in stored fuel, how those demulsifiers work, and how best to use those demulsifiers when we want to use them, especially within the overall context of how they fit into a comprehensive fuel preventive maintenance or fuel PM service plan like Bell Fuel and Tank Services. So in order to do this, in order to accomplish this goal, we're going to cover a review, first of all, of the kinds of water found in fuel and the options available for measuring and documenting water content in fuel. We will go over diesel fuel's capacity to hold water and what actually happens when that water turns into emulsified water, which is the kind of problematic water content that we will be learning more about. And then this, of course, will lead us to consider, what are emulsions? These things, fuel water emulsions, what are they? And more importantly, how do you correct them? How do you resolve a fuel water emulsion? And that means talking about demulsifier, how a demulsifier really works, how to apply a demulsifier correctly so that it will work, and how to use it in conjunction with other kinds of chemical treatment. So let's kick this off by talking about the key elements that relate to both emulsions and the need for demulsifiers, and that is water in fuel. Now, if you recall, if you've seen any of our other trainings, you may remember we've done training on this issue of water in diesel fuel. And so, we're going to have to talk about some of the same issues here that we covered there. So first we have to start by asking, what are the three forms of water, or what are the three forms that water exists in fuel as? And so, if I was doing this in front of a group of people, I'd be asking them, does anyone remember the three forms that water exists in diesel fuel as? And hopefully they would give the right answers. You've got dissolved water, you've got emulsified or suspended water, and you've got free water. So let's talk about each of those three. Normally we would start with dissolved first, but we're going to switch things up a little bit. And we're going to go to the end and work our way backwards, which means we're going to talk about free water first and foremost. So free water is, that's the water that you find at the bottom of a storage tank. Sometimes it's referred to as the water phase. Free water will form when you get addition of water, either a large ingress of water that all falls onto the bottom, or if you have an emulsion and you get additional water added to that, some of that emulsion can eventually break and become free water itself. The two phases will separate, and you get a layer of water that forms on the bottom, along with, typically, you'll get layers of different kinds of fuel water emulsion immediately above it. So we all know by now that if you have a free water phase, a layer of free water on the bottom, we know that that presence increases the chances of having microbial growth. Now keep in mind, though, that you don't need a lot of it there in order for microbes to grow and thrive. Sometimes we've used phraseology like, to a microbe, a drop of water is like a lake. Now, that may be true, but I think the more interesting analogy is one where if you have a very, very small layer of water, even let's say 1 milliliter, we're not talking about 1 inch or 1 centimeter. You have 1 millimeter of water, and you have a microbe, and we know that microbes can go from 1 to 200-something thousand in less than a day. So you have 1 microbe at the bottom of that water layer. You're talking about proportionate size comparison. That 1 milliliter of water proportionately is the same height to that microbe as Mount Everest would be to a human being standing at its base. So that gives you a little bit of perspective on the fact that you really don't need very much water in order for microbes to do what they want to do. So that's free water, relatively easy to account for. At the other end of the spectrum, we have dissolved water. This is water that is dispersed molecularly into a sufficient quantity of solvent. And for our purposes, when we say solvent, we're talking about fuel. This water content, this dissolved water, exists as individual molecules that are dispersed throughout the fuel. So they're molecularly dispersed, so to speak. They're not like droplets or aggregates of water, like in other forms of water and fuel. Now, typically, you won't be able to see dissolved water. And it's important to keep in mind that diesel fuel will always contain a certain amount of water. It may not be very much, and you may not be able to see it, but it is always there. It's only when the water content in the fuel, the dissolved water content in the fuel, exceeds certain limits that you start to encounter problems. And anytime you're talking about this kind of scenario, you have to consider the concept of saturation point. Saturation point is a physical property of a liquid. In this case, we're talking about fuel. So the fuel saturation point, it's the point at which no more of a substance can be dissolved into a solution. Now, each kind of liquid has a unique saturation point. It's part of it's a physical property unique to that liquid. Now, saturation point as conceptually, it matters here because it dictates the point at which dissolved water in the fuel will turn into emulsified or dispersed water and then into free water. It all relates to the specific saturation point of that fuel. And we should also remember that not all fuels have exactly the same ability to hold on to the same amounts of water. In other words, the saturation point is not exactly the same for all kinds of fuel samples. Now, all hydrocarbons, including diesel fuel, have the ppb to hold on to certain volumes of water, and they do that as dissolved water. We've already covered that. Like we said, there's no diesel fuel that has 0 ppm water content. Now, ultra-low sulfur diesel can approach 0.02% water existing in it in dissolved form. That is equal to 200 parts per million of water content. Now, 200 ppm is actually higher than ULSD fuels of the past. What that tells us is that, it's higher than non-ULSD fuels of the past. And what that means is that diesel fuel, let's say a low sulfur diesel that was being used in 1995, whatever, that actually held less water in it than today's ULSD fuels. So the hydroprocessing, the removal of the sulfurs actually increased the amount of water that today's diesel fuels can hold. Note also, when we say 200 ppm, that doesn't mean that all diesel fuels can have 200 parts per million of water. There's still some variance. What we mean is as much as 200 ppm. Not all diesel fuels have the same ability to hold on to the same amount of water at all times. Some of them can hold on to more water than others. So the logical question then is, well, what influences the ability of diesel fuel to dissolve water? Well, I'm glad you asked that. Let's have a look. What we just implied a moment ago is ultra-low sulfur diesel has a greater propensity or ability to hold on to water than non-ULSD diesel fuels in the past. You could say that ULSD is more hygroscopic. Now, this is because of the side effects of some of the refinery processing when they were taking the sulfur out. They hydroprocess the fuel, they take the sulfur out, they also increase the paraffin wax content, which is one thing that enables fuel to hold a greater amount of dissolved water. Also think about how ULSD is distributed, and this is more of a practical consideration. ULSD fuel tends to be produced and moved out and moved through the fuel distribution system to the end user in a shorter period of time than fuels from the past. Now, what that means, though, the problem with that is that all fuels, there's always a certain amount of dissolved water that the fuel, when the fuels are leaving the refinery, it has dissolved water in it. And if you're not giving it time for it to settle out, then where is it going to eventually settle out? Well, it's going to settle out in the storage tank of the end user. It's going to settle out somewhere unless it's burned before that happens. A big influence is temperature. Temperature is, I don't want to say it's the number one influence, but it's one of the number one influences. As temperatures increase, as you have warmer temperatures, it actually increases the amount of water that a fuel can hold. If you were in a lab and you were testing this, you would find if you have a conventional ULSD sample and you're holding it at 50 degrees, you would find that its saturation limit is about 50 ppm. But you go from 50 to 75 degrees, then that actually increases by 3x or 2x, depending how you do the math. It goes from 50 to 150. So 150 ppm. If you go up to 100 degrees, which, if you're in Florida or Arizona or someplace like that, they get 100-degree temperatures all the time. That's where you get the typical ceiling of about 200 ppm for dissolved water. So fuel that's 100 degrees Fahrenheit can have 4 times as much water as fuel at 50 degrees Fahrenheit. Now, this speaks to the concept that you could have diesel fuel and it's 60 degrees outside and it is perfectly clear. It's clear and bright. It is beautiful. But you go somewhere and the temperature drops to freezing or drops, 20, 30 degrees, like let's say you're in Colorado and you're driving up in the mountains. Well, suddenly you have the appearance of free water that you never saw before. That's because that was the water that was dissolved in the fuel. It's now undissolved because the temperature has dropped. The fuel had water content in it all along. It was just dissolved water at the higher ambient temperature. Now, what about biodiesel? As you should know by now, virtually all ultra-low sulfur diesel fuel has between 2 and 5% bio in it. Now, biodiesel, whether it's on its own or whether it's in a diesel fuel blend, they can substantially influence the amount of water that can be dissolved in that fuel. Why does it hold more water? Well, biodiesel is what they call a methyl ester. It's a polar molecule. That means it has a magnetic charge and a magnetic attraction. That means it attracts other polar molecules, which is exactly what water happens to be. So water is more attracted to biodiesel than it is to diesel fuel. So the presence of biodiesel means that that fuel will attract and hold more dissolved water than it would if the bio wasn't there. Biodiesel can also bring with it residual glycerin byproducts, glycerin being the major byproduct of biodiesel production, and if there's any trace glycerin in there, it can actually cause the formation of fine surfactants that cause the water to form finer droplets than it did before. The finer the droplets, the more water can exist as dissolved water or emulsified water in that fuel. Now, how much does biodiesel affect the fuel's ability to hold water? Well, you can see figures on your screen. At the really low, the B2 to B5, again, this is around, I think this is around 60 degrees. These are all at 60 degrees. Remember that 60 degrees with just pure diesel, no bio content, you were talking about 100 ppm of water content. If you add 2 to 5% bio, that goes up to between 140 and 170, which means you've increased it by 40 to 70% dissolved water content. If you go up to B20, you've gone up from 100 to 265, a huge increase. And B100 at 60 degrees, again, depending on other factors, you could have as much as 2,000 parts per million of water content. So it's pretty clear that addition of biodiesel causes diesel fuel to hold more water. So let's now go back to the issue of water content in diesel fuel. Now, we established that there's no bio content. Water, typically you would expect between 50 and 200 ppm of dissolved water. Now, let's say that you get water ingress and water is being added to this. You're above the saturation point for that fuel. What happens? Well, you start to get cloudiness in the fuel. Now, if you have cloudy fuel, the question might be, how much water is that fuel holding? In other words, when there's visible haze in diesel fuel, what's the likely measurable ppm of content of water in that fuel? Well, when fuel looks cloudy, the reason that it looks cloudy is because you've got what we call micro droplets of water or other impurities, or both, and it's actually refracting the light, enabling you to see it. So what you're seeing as cloudiness in fuel is actually a change in the light that's traveling through the fuel before it's detected by your optic nerve. Now, since we know that diesel fuel can hold between 200 to 250 ppm dissolved water, we know that cloudy fuel would have to have more than that. Typically, it would be anywhere between 200 and 2,000 ppm, again, depending on how cloudy, hazy, or as in this picture, how milky the fuel is. That fuel is probably a lot closer to the 2,000 parts per million. And at any rate, it's way above the amount of water that you would want to have in any kind of diesel fuel that you need to use. So if the amount of water exceeds the saturation point for the fuel, it exceeds the maximum level for it to remain in a dissolved state in the fuel, it becomes an emulsion. It forms small droplets that can become suspended as a stable mixture in the fuel. Now, once the emulsion's formed, you've got these small water droplets suspended in the fuel. And then you get more and more water. If you get more water beyond that that's introduced, during storage or in shipping or pumping, then some of that emulsion actually will change further and become free water and drop out to the tank bottom. Now, talking about emulsions, an emulsion technically is a mixture of two or more liquids that normally are what they call immiscible. In other words, normally they do not like to mix together. Think oil and water. So one of them, in an emulsified fuel state, the water would be called the dispersed phase, excuse me, and the fuel, the thing that the water droplets are dispersed in, that's called the continuous phase. And if you have a stable emulsion, then the dispersed phase and the continuous phase are together a stable mixture, which means nothing's going to happen to them unless you do something about it. And last point, as you might have guessed, with the terminology that we've used, emulsified water is essentially the same thing as dispersed water, if you ever hear that terminology being used. So, fuel water emulsions. What is an emulsion? We've already given some definitions of it. A stable dispersion of the droplets of one insoluble liquid into another. And the droplets are dispersed in such a way that they stay suspended in the dispersal medium, in the fuel, such that they are not going to drop out through the action of gravity. Now, people use emulsions all the time in everyday life in different areas. Salad dressing is an emulsion. Mayonnaise is an emulsion. Hollandaise sauce, if you like, eggs Benedict, that's an emulsion. So in order to form an emulsion, when we ask how are emulsions formed, in order to form an emulsion, you first of all need the presence of two liquids that are insoluble. You also need some kind of surfactant. And depending on the kind of emulsion, whether you want to make a microemulsion or a nanoemulsion or what they would call a macro emulsion, you may need some kind of energy input. Now, when the water you've got dissolved water and you get water content moving into the fuel and it exceeds the saturation point of the fuel to hold the dissolved water, and so, as we said, some of that water starts transitioning into forming an emulsion. Now, in the real world, it does not happen all at once. The fuel does not go from 0 to milky in 1 millisecond. What happens in real-life storage tanks is that you actually get stages of emulsions that form throughout the tank. You might have a fuel layer on top, and you might have a pre-water layer on the bottom. And then you might have multiple layers of different kinds or sizes of emulsions that are kind of stratified in between the two. You might have, what's called a nano emulsion or a micro emulsion, and these two are emulsions where, emulsions where the water droplets are really, really small. The fuel at this point, if it has a micro or a nano emulsion, it might just look kind of hazy, and the individual water droplets are only like 50 to 200 nanometers in size, which are between 1/5,000th and 1/20,000th of a milliliter. Now, because these droplets are so small, they don't need a lot of energy, or they would say they don't need a lot of shear input in order to make them suspend themselves in the fuel phase. Now, as time goes on, you've got a formation of a nano emulsion, but you might get more water that's being added, and it's wanting to emulsify as well. And so you get the formation of larger and larger droplets. Now, at this point, when the droplets get big enough, now you're going to need the presence of some kind of surfactant and probably some kind of shear input, energy input, in order to enable the larger droplets to be stabilized in the liquid without falling out. Now, at this point, you now have a macro emulsion. And a macro emulsion, typically the droplets will be approaching 500 nanometers in size, which is 1/2000. So they're like 2 to 3 times as big as the largest droplets that you have in a micro or a nano emulsion. And once you start getting water droplets of that size, that's when the appearance of the fuel changes from just a simple haze to more of a milky appearance. So, if you have fuel that looks murky or milky, then you probably got first of all a macro emulsion in there, and you probably have close to 2,000 ppm or more of water content. Milky fuel will rarely contain less than 250 ppm. And milky emulsions hardly ever form without the presence of both a significant energy input and some kind of biosurfactant that's helping keep all of them suspended. And when we talk about biosurfactants are exactly the kinds of things that microbes will produce if you've got a microbial problem. Now, one of the functions of Bell Fuel and Tank Services is detecting and remediating water content in fuel storage tanks of customers. Now, this has to be one of the essential functions of fuel preventive maintenance because water is associated with so many problems. So if we're going to do this effectively, if we're going to detect or remediate water content effectively, then you have to be able to measure the water content in a fuel sample or reliably estimate the amount of water that's in a storage tank. Now, there are different ways to do this. On a simple non-lab level, you have something as simple as sticking a tank with water paste. This will tell us how much free water phase is in the tank. It's not going to tell us if there's any emulsified water in there and won't tell us anything about dissolved water. Now, there's also field tests like crackle test or calcium hydride test kits, which One of them uses a hot plate, the other one uses a chemical package with calcium hydride, and both of those can help assess water content in the field. How accurate are they? Well, the hydride test will get you to within 50 ppm, which is better than nothing. With the crackle test, which has been done for years, the specificity, I think is what they call it. The specificity of the test really depends on the skill and the experience of the technician. Now, beyond that, there's the Carl Fisher test, and that is the industry standard when it comes to water measurement in any kind of fuel sample. Now, the Carl Fisher test has a number of advantages to it. It's not that difficult to run, and it's extremely accurate. So, how do you run a Carl Fisher test? Well, it's run in the lab, obviously. It's an ASTM test. And the simplified explanation is that you have your fuel solution and you add progressive amounts of a standardized solvent, what they will call a titrant, because this is a titration test. You add this titrant, and it will react with any water that's present in the sample, and it will generate ions. And the ions are detected by an electric current that is being, that is flowing through your sample. Now, eventually, if you add enough titrant, you will use up the water that's in the sample. You won't get any more ions produced, and the electrical current will drop, and that's when you know that you have hit the ceiling of your water content. So, Carl Fisher is the industry standard because, first of all, it can detect dissolved water even down to 50 ppm. Now, earlier we said that the hydride test can get you to within 50 ppm, but that's a little bit different than what we're saying here. The Carl Fisher test, in terms of precision, that's the term I was searching for a moment ago. Precision, you can measure to within 1 to 5 ppm, whereas the calcium hydride test's precision is within 50 ppm. And you also don't need very much sample. You only need less than a milliliter of sample to run a Carl Fisher test on. All right, and then the last water measurement test that we have on the screen is the water and sediment test, ASTM D2709. It is specified in the D975 standard, which means it's important to pay attention to. And that standard says that diesel fuel cannot contain more than 500 parts per million of water and sediment. And the test is run by taking a fuel sample, and you centrifuge it, you spin it. And any sediment and water content sinks down to the bottom of the tube where it's then measured. Now, the disadvantage with this and a Carl Fisher is that it doesn't do a good job of detecting dissolved water, and it aggregates both water and sediment content together. Nonetheless, it is still an extremely useful and legally valid measurement to have. So, we have talked about what emulsions are, how they form. We talked about how to measure water content in fuel. Now we have to start getting down to the question of how do you solve this kind of problem? How do you have an emulsion in fuel. What are you going to do about it? Within the Bell FTS program, removing water typically involves a process of combining the right chemicals with the right kind of filtration. Now, if you have free water in the system, well, that's easy enough to remove. You can mechanically remove a free water phase, and then you can run the rest of the film through a coalescing or other kind of filter to remove whatever water is left. Fairly straightforward. But if you have emulsified water, that's a trickier situation to deal with because you can't just use coalescing filters to address that. Coalescing filters will remove some emulsified water because they will essentially force water droplets together, which is what coalescing means, so that they then increase in size. which then makes them easier to drop out or essentially spin out of solution in the filter. Um, the problem, though, is that coalescing filters are not very effective at all against the smaller range water droplets, which is basically what you have when you have these nano and microemulsions. And that means it's really difficult for coalescing filters to remove enough of the emulsified water for somebody to look at that sample and say, oh, yeah, we got it all. And so it's important to realize that a stable emulsion is very difficult for any of these kind of filters to remove. And you have to keep that in mind, because you do not want to be in a situation where you're thinking that you can simply resolve or break an emulsion by running it through a coalescing filter. It doesn't work that way. There's also bag filters that can remove water. They use a kind of a chemical filtration medium that absorbs water content. But again, this doesn't remove all the dissolved water. So the best practice here, if you're trying to resolve an emulsion, is you would treat the fuel with a demulsifier before engaging in any kind of filtration process. And what the demulsifier would do, which we'll talk about in greater depth here in a moment, is it essentially it helps the water droplets fall out more easily on their own. Now, let's talk specifically about how it actually does that. And this is when we get into some of this cool chemistry speak here. So we're going to try to keep it simplified, but yet at the same time be able to understand on a molecular or a chemical level what's actually going on here. All right, so if you have a fuel water emulsion and you add a demulsifier, you introduce a demulsifier chemical into that emulsion. So it's coming in contact with that. Now, in an emulsion, you've got all these droplets that are suspended in the fuel. And the reason that they're suspended in there is because they've got biosurfactants, so they've got surfactants that are essentially attached to the water droplets and helping to keep them, locking them in place. Now, in order to understand how a demulsifier is going to fix this problem, we have to understand something about surfactants. Now, if you've been through any of the Bell trainings before with the multifunction products, you may recall an explanation of how a surfactant works. So it will help to kind of repeat that here, and then we will understand exactly what's happening here. Now, a surfactant is something that reduces interfacial surface tension. Now, interfacial surface tension sounds like a really fancy term. Let's explain in more simple terms what that is. When you talk about things, when you talk about chemicals or liquids, you've heard the phraseology. You've heard the phrase "like attracts like." When you're talking about substances, I think substances was the word I was using for. Like substances tend to attract other like substances. So when we bust out these, remember we talked about polar substances versus non-polar. Polar substances like water and alcohol are attracted to, and they mix more easily with other polar things like water and alcohol, or things like that. And the same is true for non-polar things. A non-polar thing like fuel or oil, they are attracted to and mix more easily with other non-polar things. Now, when you have a situation where you have two groups of unlike molecules, polar molecules that are in non-polar molecules, the reason why they don't just automatically mix together is because there is this thing called interfacial surface tension. There are physical forces that actually keep the molecules from combining as easily as they might. So if you have a droplet of oil or let me reverse that. If you have a droplet of water that's floating in a sea of fuel, that's a droplet of polar molecules. Now, they're all attracted to each other, right? Because they're a group of polar molecules. They're all attracted to each other. They're more attracted to each other than they are attracted to the fuel. In fact, they're not very attracted to the fuel at all, and the fuel is not attracted to them. And so Under normal circumstances, it shouldn't even stay suspended in that. It should just fall out by gravity because there's no reason for it to be suspended in there unless you add into the picture, you add a surfactant. Now, a surfactant, what the surfactant does is it actually reduces the interfacial surface tension, the thing that was keeping the water and the fuel apart. And so what that does in effect is it reduces the thing that's keeping them from mixing, which means they will mix and suspend more easily. So when you add a demulsifier in there, the demulsifier attacks the surfactants, or I won't say it reacts with them, but it goes to where the surfactants are, and it basically negates them. It deactivates them. Once that's deactivated, that interfacial surface tension thing comes back into play. Those forces are restored. Now the water droplet is no longer attracted to the fuel like it once was. The love has gone, and so it will settle out naturally like it was supposed to. So when you add a demulsifier to an emulsion, the micro droplets will start falling out of fuel like they're supposed to. They will also coalesce, or another term you'll hear is flocculate. They will flocculate, which means they start aggregating and sticking together. They form larger and larger droplets, and as they get larger, they separate out even more easily than before. So that's how you would treat that. That's what you would use to resolve an emulsion. Now, Bell Performance has two product formulations that contain a demulsifier component. One is Bell Demulsifier EB, and the second one is Dee-Zol Tank Formula EB. So the question we would ask is, what's the difference between the two? Well, they have, first of all, they have different treat ratios. Dee-Zol Tank Formula EB has a 1 to 2,000 treat ratio, which means effectively it's 500 ppm effective treat rate. Demulsifier EB is just pure demulsifier, and that means it has a much lower treat rate, anywhere between 20 and 100 ppm. So, could be as many as 5 to 25 times lower than Tank Formula EB. Since that treat rate is so low, it's so concentrated, it stands to reason that Demulsifier EB is not intended to be a consumer product. It's not intended to be something that somebody's going to stick in their gas tank. Instead, it's intended to be bought and used by B2B fuel distributors and people who have large fuel storage tanks who need to do something about an emulsified water problem. So, what's the best way to use a demulsifier properly? And can you use it improperly? Well, yes, you can, and that's why we need to know the best way to use it properly. First, like lots of other chemical treatments, demulsifier only works when it comes into contact with what it's acting on, which are the emulsified water droplets. And that means you have to introduce it in such a way that it comes in contact with those things as quickly as possible and stays in contact with them for as long as possible. The best way to do this, there's multiple ways you can, but the best way to do this is by a direct injection into the emulsion. However, not a lot of people have the ability to do that. Most people don't. So for those people, the recommendations, you follow something like this. You would, you'd introduce your given treat rate of Demulsifier EB or Tank Formula EB. You would introduce that into the fuel phase, and then what you do is you would circulate the fuel for about 15 to 20 minutes. Now, you would not circulate it at a high velocity. You circulate it at a moderate speed, and this is important. It has to be a moderate circulation. If the tank's larger, you might want to do it for an hour. You could also, at this point, introduce other treatment chemicals, like if you're using biocide at the same time, if you're using a sludge dispersant, you could also introduce it at the same time. Your circulation period ends, you stop the circulation, and you would leave it. You would leave it for 1 or 2 or 3 hours, 2 to 3 hours typically. And what that does is that gives time for the water droplets to start falling out of solution. It gives time for them to coalesce. It gives time for them to flocculate and stick together and start dropping out of solution. Now, the fourth thing, you now have a free water layer at the bottom because the emulsified fuel, the emulsified water, has separated out and become free water. Then you would mechanically pump out the free water and then proceed with your other mechanical processes. Now, we said that it's important to circulate moderately. The reason why you don't just want to circulate the heck out of it is because it is definitely possible to re-emulsify dropped out water back into the fuel. A demulsifier functions to break a fuel water emulsion. It doesn't do anything about keeping that water from re-emulsifying back into the fuel. And you don't really want to undo the work that you did. So that's why you circulate it moderately for 15 to 30 minutes, maybe up to an hour, but that's really all you need to get it optimally mixed into the fuel, so to speak. Now, how do you know that it works? That's the question that follows from how do you use it. How do you use it, then how do you know that it's worked once you do use it? Now, the thing we have to say is that demulsifier use or resolving fuel water emulsions is as much an art as it is a science. In most field situations where you encounter a fuel storage tank that has a volume of fuel water emulsion, in most situations, it's not possible for the service technician to have every piece of information they need to define everything exactly as well as they would like. They have no idea how much water is in the tank because they don't know how much water is emulsified in the fuel. They may not know exactly how long they have to circulate it for. They don't know if there's any water that's hidden in certain areas of the baffles of the tank design. Typically, they would need to know things like how much volume of fuel is in the storage tank. Well, you can know that. They would want to know the total volume of fuel water emulsion. Well, they're not really going to be able to know that. They're going to want to know the concentration of water in the emulsion. Don't have any way to know that. So, given that it's not possible to know everything, you have to make some judgment calls. And so for the majority of field use scenarios involving a demulsifier, successfully using it means you start from a reasonable starting point, like adding enough baseline demulsifier, using best practice application methods to get it in there, and then observing this is important, observing the results and then reacting to what you see. Sometimes emulsion breaking is not a one-shot fixes everything kind of thing. Sometimes you have to do it more than once. Just as with biocide application, there may be some situations where you have to retreat. I mean, that's just the way it is in the real world. So what can you do to maximize the effectiveness of your demulsifier? Or rather, actually, wrong question. Once you use a demulsifier, what would you expect to see to show you that it did what you wanted it to do? That's the question that we're really asking. Well, there's a couple of things that would be fairly obvious indicators. The first one is that you'd see the presence of a greater free water phase because you removed as much of the free water before. There may have been some left, but by and large you removed as much of it as you could, and then you added the demulsifier and you came back, and 8 hours later when you stuck the tank again, you instead of it barely registering on your stick, you see that you've got a 3/4 inch free water phase. That used to be the water that was emulsified in the fuel. You know that the demulsifier has done its job. What a service provider might also see is that they might see a change in the amount of time that it's taking for their filtration process to clean up the fuel because the fuel water emulsion is no longer there or it's greatly reduced. And that in itself is going to make it easier to resolve and clean up that fuel. And they might also be able to document a longer filter life with their coalescing filters. So as we start to wrap this up, a fair question here: protocols for use with other kinds of chemicals in the FTS program. What is the best way to use the emulsifier if you're using it in conjunction with other FTS-related chemicals? So before we answer this, we might ask the audience, we'd say, well, what other kinds of chemicals could you possibly use? Someone might say, well, biocide, sure. Sludge dispersant, yep. Water controller, yep. Dee-Zol life, stabilizer, yes. 3 out of those 4 are actually correct. The DFS is the one we threw in there as a curveball. You actually would never use DFS with the emulsifier because they have conflicting or antagonistic effects. They would keep each other from working. So DFS is something you would never use with the emulsifier. But what about Belicide? You need to use both Belicide and emulsifier at the same time. Well, you could add them together. Add them at the same time as add the biocide at the same time as the demulsifier. There's no reason why you can't do that. Tank treatment SDF. Well, if you've got significant sludge content as well as emulsified fuel, the usual recommendation is, remember, vacuum or mechanically remove free water phase, and you would also do that for the excess sludge. So you remove both of those. Then you would add the SDF and the demulsifier together, and you'd circulate it, and you'd leave it. Then you would mechanically remove whatever free water has formed and whatever thinned out sludge is still present in there. And then you would proceed with your filtration. Dee-Zol life. Dee-Zol life as a fuel stabilizer is typically added at the conclusion of a treatment protocol. So use of demulsifier doesn't really affect when you want to add Dee-Zol life. So now, at the conclusion of our training, we're now experts in emulsions and what to do about them, right? Well, okay. Nobody becomes an expert at anything overnight, but the kind of information that we've been talking about here over the last hour is what is going to help the Bell FTS program set itself apart from the other ham and eggers, so to speak. So what do we want to take away from all this discussion? Well, we start out by discussing that water typically is found in 3 forms in fuel. You've got dissolved water, you've got emulsified water, and you have free water. And we also learned that different kinds of fuel have different tolerances when it comes to holding on to water. Now, we learned that you can measure water content a number of different ways. There's the simple method for detecting free water, which is like sticking the tank. There's also a more standardized way, like the Carl Fisher titration test, or even the water and sediment test. We learned that emulsified water forms when you have dissolved water and fuel and you get additional water added to it such that you exceed the saturation point for that fuel. We also learned that different kinds of emulsions can form within a fuel tank, anywhere from a nano emulsion or a micro emulsion that's just like a simple haze, all the way up to really serious milkshake emulsions. We learned that coalescing filters by themselves can rarely resolve an emulsion without some kind of help. You need a demulsifier to force the suspended water droplets to separate out of the fuel as free water. We learned that proper application of demulsifiers is really important, because if you do it wrong, you can just recreate the problem by re-emulsifying the free water back into the fuel. We learned that the best practice application would be that you would remove the existing free water. You would add demulsify, and you circulate and allow it for time to work. Then you would mechanically remove the newly freed water and then proceed with the rest of the job. And then lastly, we learned some ways that demulsifiers can be successfully used in conjunction with most other FTS-related chemicals except for the one, which is, of course, the DFS+. So that concludes our training today on demulsifiers. If you have any questions, then please contact me at Bell Performance. Once again, this is Eric Bjornstad, Technical Information Director with Bell Performance, signing off, and we will see you next time.